Yeah, welcome everybody back to Lecture 9 from High Performance Computing. Lecture 9 is about accelerators and graphical processing units. And we have seen in the first part of the lecture really the idea, what is the difference between those many core architectures and the multi-core architectures. So the multi-core architectures have a couple of very good cores, very good high single thread performance and cache hierarchies. And what you also have seen in the video, this is of course powerful, but in a way it's limited because of the parallelization. We said that multi-core chips face the challenge of the heat per chip, so we cannot just put more and more on that chip. We have a heat problem there and limit in performance. However, the idea then was, why not having, let's say, moderate cores in terms of speed and clock rate, and then have, let's say, many of those. That's where the term many core comes from. So initially people have done hundreds, but now we see really with streaming processors, CUDA cores we have seen in the hundreds, now we see thousands. So essentially saying that this many core is exploding, but also the technology around. We have seen HBM, the memory is quite important to fuel the GPU constantly, essentially with data, because that's where it's really good at. It does, let's say, not so smart operations, but it basically can do those smart operations, not so smart operations, of course, in order of magnitudes of scale. So basically, as we've seen with painting the Mona Lisa in the last video from part 1 of the lecture. So here the power of GPUs is really best explained. It's a parallelization scaling up very quickly, essentially among all this graphics processing unit cores. And then we have also seen that actually you have not to stay with one GPU to do and to leverage this performance, you want to interconnect it. We have seen that the Summit system or the Jubal system have thousands of GPUs these days in high performance computing systems architectures. Of course, they're limited essentially with NB links and SD switches across, let's say, a couple of nodes, but then there are frameworks with Horowat essentially, and then also frameworks with deep speed you can leverage then to also go beyond essentially these islands, as we would say, and go much more broader in scale. However, now this is also a little bit of the second part of the lectures, where we talk about now what is the GPU libraries, which makes sense, the programming models which are used, so how you actually program a GPU. Of course, also just one side remark of the first part of the lecture is the same for the second part of the lecture, really. You would say that normally would have 3 to 4 days a GPU training in one of the centers in Europe. For instance, would that be Barcelona, Jülich, Munich, or basically Stuttgart? They all have their different tutorials, trainings available, essentially do really work with GPUs to understand them. So my lecture here is really just an introductory lecture to show you a little bit what GPUs can do, how they are different to multi-core systems, and how it's really impacted the field of GPU libraries existing today. So coming back again to many core GPUs, let's have a little bit of a, let's say, a case study when we want to use essentially libraries, when we want to use essentially GPUs in parallel with some application. And one of the smallest applications, I think, is very clearly here demonstrated when you think about this matrix vector multiplication we already had now several times. When you put that to a GPU graphic cards, you will see it immediately that this nice parallelization is really possible. You see here that essentially all these elements of this first string can be computed completely in parallel, independently from all what's happening in the other processor cores, right? So this is a nice thing. All you need to know is at the end, you probably would sum up, but still you can essentially then compute this by using this color encoding here a little bit independently. And this independently is a very important notion for this GPUs, because all of these multiprocessors are not really talking to each other very much. Much more, they are essentially used to use the same instruction again and again on different data. And this data comes out of the device memory, hence here the fueling of the matrix and of the vector data in terms of real mathematical numbers. How you would do it is then very clear. You first, step 0, you really have to load. Then via the main memory of the CPU, the host CPU as we would call it, then essentially the data to the device memory. And this includes also here and there before even uploading the kernel. So what should be done with this multiprocessors, right? We call that a kernel right now. This may change in the future, especially in the light of the fact that we would have different vendors playing now a role in GPUs. But essentially everybody will understand these days what you mean with really having a kernel then uploaded. But the kernel is not enough. Again, the emphasis is on data. So how you fuel the kernels that you run here, which will be then executed in massively parallel endeavors, giving really hundreds of thousands of these different GPU cores. In step 1, then, we would say that each of these GPU cores has this column matrix, B, what we would say maybe B part, and then also, of course, has an element of the column vector here, the C part, where you can then program it, as I said, and then will be executed as a color code here. And this means that also in this step 2, everybody works independently on the problem, right? Once I have chunked it up and basically put it onto different elements in this processors, then of course this is independently computed, which is nice in order to do this vector scalar multiplication. And then in the end, you basically have then just that the GPU core has then a result of this vector A. What we would say is just the A part, but it's also essentially a vector that comes out there out of the matrix vector multiplication. So essentially this A part then would be, of course, thinking about also then bringing it basically into the device memory from all of the different processors. But then the idea is also that the CPU would then catch this in the main memory, so to speak, and then basically has it available as a CPU. So in a way, you would say how you would use an accelerator. You would use it for very specific problems. You would not think that the whole application is maybe using a GPU. Mostly it is that you would like basically perform some specific mathematical operation where essentially a GPU is very good in. And as we said earlier already, matrix multiplication, matrix column vector multiplication you see here, these are all examples which can be independently computed here and there, and then beautiful to be parallelized in GPUs. Now, another great impact essentially is when you look at the deep learning area. And this is, of course, a big area because it's why we also have, of course, lecture 10 and practical lecture 10.1, practical lecture 10.2 for it, where I really get some insights about this deep learning, how it leverages GPUs, how you use distributed learning. So just some appetizers really that deep learning has made this technology available and what it constitutes. The first thinking of people when they hear deep learning is that people know a little bit about neural networks. It's what we've done in the past. So here's a feed-forward network with 4 hidden layers, an input layer, and then also an output layer, and 4 hidden layers. And essentially, this was how basically neural networks were used before. So everybody had here layers with different neurons inside and a fully connected network where each neuron is interconnected to each other. Now, this situation changes. So deep learning is not just putting more and more hidden layers. That's not the idea. So the idea of deep learning is quite different. You would have very specialized deep learning architectures for very special problems. So one example is here for image recognition. There we have actually seen that convolutional neural networks, as they're called, and you will learn in lecture 10 and the practical lectures, is really optimized to get features out. So we do feature extraction out of these images and then perform a classification of this is a 3, this is a 4, this is a 5. So this is an example with all the numbers you can put in. It's called handwritten characters, and it's a handwritten character recognition problem, of course. But you see also here the problem that arises in this. There would be some which you can really not learn. However, the deep learning will do a very good job in this. But you see also, although it's perhaps deeper than we would call the shallow networks of neural networks, it's still not the same architectures. It's not just neurons. Here we talk about so-called feature maps. We call about convolutional operations, downsampling, Every of these layers has a specific function and specific property. And it's basically not really just deeper. It is really using different layers of very specific ideas and approaches. And the same is actually true if you do time series analysis. So for time series or sequence data like languages, right? Language, text is sequence of characters. So essentially also there you have long short-term memory, you have gated recurrent units, you have a very specific architecture to deal with the sequences. It's a large field these days, and the takeaway message why we bring this here in this lecture is it has been enabled largely by many core technologies. So doing deep learning on CPUs is not really recommended, especially if you have cutting edge CPUs where you see initial architectures maybe like here or AlexNet that were convolutional neural networks were small. Today we have residual networks, ResNet 50 I will show you where lots of parameters have to be trained. And this doing on a CPU is really unthinkable. Before we go a bit more into this, let us review a little bit how that looks like when we now thinking again of deep learning versus the neural networks we had before, which was starting by perceptron, things you will learn more in lecture 10, but just as a first appetizer and a bit of understanding why parallelization is now so key ingredient. Okay, so that was quite an introduction to deep learning, but it is a deep technology that is essential for GPUs these days. It is, of course, also driving the architecture design from a certain perspective because many people just using deep learning with GPUs. In other words, also you can see, especially for NVIDIA's perspective, in the moment that this is, of course, a return of investment from all the technology development where we see new GPU architectures. We discussed it, right? We saw Kepler, then we saw Pascal, we saw Volta, now we see Ampere. So this is, of course, the idea that NVIDIA also has money for inventing this. And of course, also then the people that really buy it, the organizations, the HPC centers, the industry. And this is a very good example where one application field does some co-designing, so to speak, of really hardware technology, because we see also that the elements that you push through here are called tensors. You have a multidimensional array of some sort. It could be also 3D convolutional maps and 3D convolutional networks, right? This is just 2D. But if you think about, you can have RGB as a third, let's say 3 dimensions, right? RGB build image. So, and then you have suddenly 3 dimensions you pull through, and you can do this as a 3D convolution operation here through. But the key message again is a very interesting field, and we will learn much more in lecture 10 about. We will also learn that essentially the idea of this tensors, of working with it, has been influenced also libraries that leverage GPUs quite successfully, and which is important, of course, for the drive in the field. So when you think about artificial neural networks 10 years ago would have been implemented for large data sets, maybe with MPI and OpenMP, because memory was limited. There was no GPUs largely available for general purpose computing. And then essentially you think about, I have to implement all from scratch. But today, what we see is there's an enormous set of libraries, enormous set of frameworks and tools available for doing deep learning. There's PyTorch, there's TensorFlow, there's Keras, which is actually often used on top of TensorFlow, while TensorFlow is a more low-level framework really to work either on CPUs, but also, of course, much more effectively on GPUs here. You essentially have then also Keras working on top of that framework to essentially make it a little bit more simpler, where you see often that you essentially see in TensorFlow an operation mostly oriented really on the real nature of the tensors you ship around, while Keras is really more in the idea of thinking about these layers and the structure we have seen, for instance, also in the videos, with the different layers, with the different feature maps you want to do. So a little bit more used for training and tutorials often. So it also should enable much more faster experimentation, as you can perhaps do with TensorFlow directly. That's why also Keras is so successful. And actually also these days, Keras is part of the TensorFlow distribution and also heavily used in data science today. We will make some examples, or we'll also show you some elements essentially in lecture 10 and its practical lectures. Here's an example that we will talk about just to motivate also that, of course, essentially deep learning and essentially then the uptake of these GPUs and why it's so successfully again has been driven by big data and the availability of large data sets which are available now. So here you have an example of satellite imaging, which we will explore in lecture 10, really to make an application field example, where you have a satellite taking essentially 24 hours a day, essentially always images and basically measurement data from the space on the Earth. But this is usually not just essentially a 2D picture, what you get out of this. So this is really hyperspectral and multispectral data capturing different spectral channels essentially. Then, and with this, you are able to look inside the Earth, and you can, with this, already have, let's say, an interesting set of data that you want to analyze. You want to see where are irrigated areas of land, where is water, where is forest, where are essentially areas where it's maybe permanently irrigated land, where are rather vineyards, or basically where it's just dunes or even sand beaches is maybe sometimes disappear when flooding, or basically the idea of other natural disasters come into the game, right? So what we have seen there is also, of course, interesting tsunami analysis, which is possible. However, this is a broad application field. The key message again is it is really driven forward now by deep learning, especially if you think about these feature maps we have seen in deep learning. So capture the essence of the surroundings. So this is an important factor that we also will leverage and look at in lecture 10 again. And here's really one of the interesting motivators to come back to lecture 9. So when you have seen the data set before, it's quite some data set in terms of volume. But what really requires GPUs here is essentially this 25.6 millions of trainable parameters. This is a way of doing a convolutional operation here in one box, but you see we have a very deep networks, and we have here essentially then the skip connection, making it a residual network. But this is something where you have so many parameters to train that a single CPU would be out of question, and even one GPU would be too slow. So we will motivate a bit also why we really have to interconnect GPUs here. In remote sensing, this is now really modus operandi, especially for the more recent data sets that you want to apply deep learning to. Of course, also the architecture plays a good role. So ResNet 50 is a kind of good trade-off between accuracy, depth, and the number of parameters. You can go deeper, you can basically do more shallow. Of course, it's just one, let's say, architecture that stands the test of time. But essentially saying that, of course, nobody tells you that this architecture is the one for your application problem, right? So you have to find the right architecture. You have to do architecture tuning, optimizing, similar as we discussed in the last lecture 8, where physical codes maybe have to rearrange their MPI strategies in terms of finding patterns which are perhaps not so good in terms of performance. We have here a similar problem of saying you cannot just think that when you have an application problem in the data sciences like remote sensing, you have ResNet 50 and it works directly off the shelf. There's still lots of different parameters you have to tune. There are hyperparameters like which optimizer to use, things which we'll learn later than lecture 10. And as such, you would not run it once, right? So you would run it many times to really find out the good parameters. And with this, you need just more and more of these GPUs in parallel. In order to do this, you can leverage HPC. You can leverage systems like the Joule system we have seen here. This is part of the older part of the system from the Joule's part, and we see here there's still the V100, not the A100s inside, and still we managed to interconnect them and use basically this ResNet 50 across 24 nodes, which each of them having 4 GPUs. So essentially we could train this ResNet 50 with 96 GPUs in parallel. And as such, you can see we have this interesting speed up, right? Which is now essentially something you can do always when you have a TensorFlow problem, and using it basically then on different GPUs together. Of course, this includes also the data that you have to distribute, and hence you need a framework for helping you essentially of bringing us this basically down and basically keep it also from a certain perspective user-friendly for an application developer, in order not to basically do this all in a more manual fashion. Hence, we use a framework here as an example called Horovod that is using distributed training. So distributed training is actually something which we have a complete lecture on because it's not so simple. As of course, also the parallelization of many application codes in physics is not so simple. We have the same situation in distributed training. There's model parallelism, data parallelism, and of course, it's not so easy to always think about you can just throw more GPUs on it and then it will automatically speed up like we have seen here. So there are lots of problems, and Rocco Sedona in his practical lecture 10.2 will actually make the case for it once we have learned in practical lecture 10.1 by Gabriel Cavallaro what deep learning is really. He will also talk a little bit about deep speed, which is another framework, more recent, coming out doing very similar things. However, for us, it's interesting from the perspective of the HPC lecture that Horovod is using MPI all reduced. So you can see still MPI, our glorious message passing interface that we have learned in the beginning of the course, is essentially also used in this area. It's a good example for this inter-process communication taking place. And how it is used essentially is in so-called gradients exchange, which actually is capturing the training process. When you do it in parallel, of course, you have this on different nodes, and you have to, at one point in time, then exchange what you really learned from the different data that came through. But more of these details will be then essentially given in practical lecture 10.2. So I don't want to say here all about this as well. And then, of course, you think about that this is a quite successful way of speeding up all of this, but at the same time, not losing accuracy too much. And I think Rocco and Gabriel will make a case for it. So I skip here now to think much more again about the implementation aspect. So how I program such a GPU, right? If I'm not having directly TensorFlow available, if I'm not doing this kind of sciences, you see here that essentially GPUs have conquered these days almost all application fields you could think of. It's modus operandi by analyzing videos. For deep learning, data sciences, data analytics, GPUs are also a key ingredient these days. Even in classical machine learning, we have seen now that GPUs actually can help significantly. Classical machine learning meaning also shallow neural networks maybe, where still GPUs can help a lot. Scientific computing in general, you see here a couple of interesting, let's say, libraries, which many of those we will actually introduce as a second part of our course when we start more the application fields by the application experts. NumD for molecular dynamics, GROMACS, Ember, we already basically have here in the course. And there are also others in different areas of sciences. And you see all of them are more or less ported now to new GPUs. And by doing so, it's mostly that they adopt the CUDA architecture, the CUDA parallel programming environment, which is called Compute Unified Device Architecture. And it's called CUDA code or CUDA kernel that you would upload to a GPU from NVIDIA. Of course, AMD will change this, and we will have also a video later on the AMD details to show you a little bit also the different perspective which is coming up by using more and more of the AMD Instinct cards or basically also new vendors. But essentially today you would say mostly you would have to write CUDA kernels that you then upload to a GPU, and then also think about the data that of course these kernels should work on. In a way, the idea of this is a bit similar like you had in OpenMP. So we have a scalability, which is essentially unlimited, as the number of threads are not really always very specified in OpenMP. You would program it against, let's say, an undefined set of threads. But with GPU devices as kernels, you would have the same approach, essentially. You say that the program can be really for one thread instantiated on many parallel threads somewhere in the GPU space. And any number of processors could be running on this, and there's no new compilation of no defining how many threads should actually work thereon. So the best way to visualize this is then really going maybe in a stepwise fashion through this. And before we do this, just again, I think it's important to point out that firstly, it is not like gaming with this graphic cards, right? So you have seen the GeForce environment, and many of you would know that the GPU in GeForce stands for entertainment, computer games, something like this. Also in engineering, there's a certain area called Quadro with, doing manufacturing, computer-aided design, and so on. So they have also Quadro cards, but Tesla is in the, let's say, overall area where high performance computing plays a large role. So really intensive simulation sciences, computational fluid dynamics that we will have also in one of our lectures, which actually leverages codes like OpenFOAM, for example, right? Or as we have also seen molecular dynamics with GROMACS, with NumD or Ember. So these are all very compute intensive problems. And we will see, for instance, in the CFD, for instance, that we could throw for direct numerical simulations so many computing on a problem that we are having today not enough computing to solve it. So using OpenFOAM or ANSYS Fluent for CFD applications uses certain different tricks in the, let's say, numerical simulations by basically using then a different approach. But in the end, if you want to have it completely correct, you would say you need this direct numerical simulations, which are very hard to solve. And with this would require computing without, any limits. So we're not there yet, but also shows you and demonstrates that high performance computing is really needed, especially if you think about also the day-to-day impacts that we have. You see here VARV, which is one of the lectures we have later on, basically covering the weather and research forecast that essentially from your daily look in the weather forecast that you want to know. Of course, there are different codes these days as well, but essentially high performance computing is fueling your weather and research forecast every day. Now thinking about again this stepwise approach, right? So now we know a lot about GPUs. We have a specific architecture, and of course this is now something which I abstract here a little bit from, let's say, a real CUDA specific architecture on a specific GPU. Here we are a bit more general of really showing you the processing flow, how you work with GPUs, and essentially thinking about how that could work in an abstract manner for many different architecture types. And if you want to know more, I think this is a very good resource from one of my colleagues at the ULI Supercomputing Center who done a GPU course here. So if you're interested in this field, I really encourage you to go there, or basically use a praise training website that we had already in one of our earlier courses, where you really then have also more and more GPU courses appearing. But if you, let's say, want to know how it works from a certain perspective point of view as an application developer, you start with your CPU, which is your host CPU, right? But we also learned that the host CPU has this device attached, what we called accelerator, which is this interesting device. And of course, you can transport data back and forth. And we said the device memory and the CPU memory is quite important. But you see also the different thousands of small cores or streaming cores, as some of them are called today, tensor cores. And of course, the GPU itself would have a scheduler to manage all of this. So this is luckily that you as a CPU, application developer don't have to specify it's now landing on this particular core here or on this particular CUDA core. So in a sense, you would do something now, what we will see in the next step, to really fill these systems with some application logic, but the scheduler will help you to really manage all of these hundreds and thousands of threads. The interconnect is there to connect essentially to the system, and we would have a little bit of a cache, but of course the memory, as we said, from the device is much more important. So overall, you would say your goal is to offload some problem. And that's how it's called, GPU offloading. You would say you start with a CPU problem, you work in an MPI OpenMP problem as an example, and then you would find something which could be mathematically conveniently used in the GPU. So you basically offload this, you have a kernel that works in the GPU on this particular problem, indeed very fast, perhaps much more faster than the CPU could do. Remember the Mona Lisa in the first part of this lecture. So then you would use a GPU just to accelerate some parts of your program. That's why it's also called accelerator. It will not solve everything. It's not a general purpose idea of using a GPU. It's really offloading for particular problems, and then you're back in the CPU. So the processing flow will always be CPU, GPU coming back to the host CPU. So then the first thing you have to do is essentially then transfer data, as we discussed, from the CPU to the GPU memory. This is of course important because all these tensor cores or CUDA cores or streaming cores, and many variants today, they need something to work on. And we have seen they do, let's say, not so smart operations, but they do them very quickly and they do them heavily in parallel. And so this is of course substantially important then that you can have a lot of data to pull that through. Also, let's say having it with a high throughput through these cores in order to fill the GPU always with some interesting data to work on. So it's something where you first have to think about, and then the CPU is essentially responsible, of course, for this to transfer the data there. And also what I said also earlier, transfer the program, right? So we have to think about the kernel that we want to upload to this system in order to schedule this then across all the different CUDA cores. Once you have loaded this program or loaded this GPU program, which is now really helping, or where the scheduler really is helping, you essentially have all this kind of streaming cores worked on different types of data in their own memory, right? Which is essentially the device memory. So in this point in time, the CPU memory becomes essentially meaningless. So this is really just acceleration of work, which is now completely defined in the space of the GPU. It is essentially done there. And of course, by having the memory, as you know, you would say this is all a shared memory approach, right? All of this is happening essentially here. They share the memory of the GPU and can write back there. So this is the second big part, essentially, when you want to do the processing flow. Then the third is, of course, once you have computed all of this, to get the parts out of the device memory. So you have to have the step now back to the CPU memory, to the host memory, and really to transfer the results that you have so long computed in the GPU to either work further with it, or basically that was all you have to do. It depends on the application, but essentially you have to bring it back to show it, to write it to disk, to do something with it. So one idea of an application, and you can imagine now I could go on and go on in all the different fields of sciences you would have a GPU impact today, but here's a very good example of the so-called CUDA BLAS library, which essentially BLAS stands for a basic linear algebra subroutines. It's a collection of around 150 routines really for linear algebra, which are very easy to understand, often incredibly often used. And one of them is sexpi, which you know here, is essentially defined as nothing else than saying it's a single precision of A times X plus Y, right? And S for single precision. So this is a very commonly known problem, and you can see here a simple CPU example version of it, which is nothing else than leveraging a for loop here in order to get this A times X plus Y implemented. So of course, there's a library for this in CUDA, and you can have this now in very different libraries that, of course, CUDA is a toolkit of choice. However, in the future, we might see that changing. And this is, of course, then here the second element that you see, the OpenMP toolkit, which is essentially now the next generation that will come out there that maybe are independent more from CUDA, right? In the moment, we would say that CUDA can still get more performance out of it. It is more feature rich for NVIDIA GPUs, but OpenAC code can in theory then also be used on AMD cores, AMD GPUs, which is of course very important for an application engineer, because otherwise you have to now maintain a source code base of a CUDA version and of an AMD version, and God knows what will come up in third or fourth vendors on the market very soon, which are also basically offering you GPUs. And once your HPC system you have access to is actually having such a GPU, there's no way around it. You cannot say, I don't like CUDA GPUs, I want AMD GPUs. When your HPC system is full of CUDA GPUs from NVIDIA, then essentially you have to go that way. Otherwise, you basically have to switch the systems. So here's another idea of how this now works when you think about the CUDA BLAS and the steps we just said in the stepwise approach as an example, and to connect back to the abstract connections or the abstract processing flow really of working with GPUs in context with the CPU. Again, after initialization here, which is a little bit of pseudocode here, pseudocode, but you have some handle, you have initialization. You would allocate GPU memory for a certain problem, and you see here that we use this X and Y, which apparently in sexpi makes a big role. So we allocate the size of these arrays, and essentially, as we said, as one of the first steps is basically copy the data to the GPU, right? So now what we are just doing is the size of the data we have in the device memory will be now copied and uploaded to the CPU, to the GPU, and then we call essentially within essentially this environment of the GPU, then this BLAS routine that we said sexpi in this basically device X and device Y memory space. And of course, the GPU will take care that this now actually works. And the scheduler that we have seen, right, working on this kernel and working on this cuBLA sexpy. So coming back then with the results to the host, we are interested in the newly computed y, if you remember, because y is nothing else than essentially a times this x plus y that then equals back to y. So essentially you're interested in the results of all of this and then free the handle. It's just, of course, one example how you could program such sexpy and using then accelerators for it with a cuBLA library. Another interesting example, because it also connects back to our lecture 6, is then of course the new developments around OpenACC. You see here essentially a traditional code that you could already imagine is OpenMP, the pragma statement with a sentinel, basically saying what you want to do, distribute, or OMP parallel for loop. And essentially remember that was actually how we programmed OpenMP in lecture 6. And essentially now what OpenMP was giving us, it had the master thread, and at some point in time it was forking different parallel threads and then joining them again. And in the same way you could imagine is now essentially the way how you would program a GPU. It's very similar, right? You would say you have a master problem working on some application problem, and then essentially at some point in time you want to accelerate certain mathematical operations. You want to offload this to a GPU by using some kind of a kernel. So essentially here you would use large parallelization, similar aspects like you learned in pragma. Here pragma ACK would be then the idea of OpenACK to just complement essentially the OpenMP statements with some more elements. Here you see copy out of y and x, because we know in sexpy that plays a big role. We computed them in parallel here in this loop, as we know already, and then essentially have here this sexpy operations with a scalar a, or here is an I, times x plus y, which is a sexpy, and then essentially computing this heavily in parallel by actually using OpenMP constructs more or less, complemented with the ACC. But before that, of course, we have to copy, this is important, then essentially here the data to the GPU. So in a way, it's more easier for users, for application developers to follow the way of parallel computing, because OpenMP is a kind of standard really in the community. And you see here different ways how you can do it. It's basically that the transfer and all the ideas is really hidden from the programmer, which is very good. We have kind of an accelerator model, which is very good in OpenACK because it's so similar with the compiler directives to OpenMP. It's straightforward to adopt, and essentially then the device code is then very simply uploaded, as we discussed already, from the device, from the host then to the device, without having large overheads to do this as part of a programmer. But this is not an OpenACC course, so of course now you can imagine you have a CUDA course, you have an OpenACC course, you have maybe also a HIP course, because we will see also there's another idea coming up of actually abstracting from all the different vendors. Now just saying you that essentially here is a demonstrator for this change. There's a strong market dominance from NVIDIA. There's no secret about this. You have seen that in the top 500, you see it essentially in HPC, and in many servers, which maybe even not are directly HPC, but doing, let's say, moderate computing in some banks for transactions and so on. However, there's the AMD Instinct GPU coming along, and MI100 is quite cutting edge. I have a video with me here today that shows you a little bit about it. That's why I don't have so much details on the slides here. But the key message to take away is that it is adopted. You see here the Lumi architecture of the supercomputer in Finland currently being built, which would be one of the important architectures and HPC systems of the Euro HPC joint undertaking, which brings together whole Europe. And here we have a supercomputer by quite some fractions of Europe finance, where also Iceland plays a small part in it. in the Lumi process, and we have a GPU partition which is essentially adopting the AMD Instinct MY100 cards. So here you have already the porting problem that all the CUDA applications might not work so quickly. Of course, there's community work along these lines, how to basically port quickly to AMD GPUs, but still we can imagine this is not so simple. And then in further orders of scale, you will see that the Frontier supercomputer, which should be maybe the first exascale system we really see, there's still a question mark about this, but we will see maybe 1.5 exaflops of peak processing, which should be also then using not only AMD host CPUs with the EPIC here, but also the AMD Instinct GPUs. And of course, CUDA is not really supported by the AMD hardware. And you will see also why in the video later. Still, it's used HBM2, so also the same memory setup you see in NVIDIA, and has, of course, also thousands of GPUs. So we see here around 8,000 stream processors working in parallel, essentially then on this GPU. And this is just, of course, then one GPU. And of course, think about that systems like Lumi or basically like Frontier will then have many of this AMD Instinct GPUs included. And that brings us to the motivation now of one of the last lecture slides here. Today, we need perhaps a heterogeneous compute interface for portability, short HIP. In other words, you have CUDA codes, you have AMD codes, and now what you need to do is to abstract from all of this and have maybe a HIP code. And you see here, it's very similar to CUDA right now. So it's really not much magic in the moment because it was mostly also, realizing CUDA. But in the future, we see that, of course, also AMD GPU should be supported in this. And you see some warp, you see some, which is important art. When you CUDA program, you need to know what a warp is. And then basically you see there are different terminologies in HIP, but essentially the same ideas how to do it. And then the idea would be that you implement in HIP, maybe using C++ as a runtime API, and then you can actually have portable codes for AMD and NVIDIA GPUs at the same time, which would make it easier for application developers. And of course, then also something which AMD is pushing very much in order to get, let's say, also codes which previously just run on NVIDIA, now executed on their own AMD, let's say, GPUs. Here's again this HIP and CUDA example, just for your reference. You see here, many of these are just naming conventions, a little bit changes when you add vectors here and so on. But the idea is, again, very similar. Allocate the memory, copy from the host memory to the device memory. By now, you know the story very well. And after that, you want to basically get essentially back to the host with all of the memory data you computed. So I think this would be ending up in many repetitions because the idea is, very similar how to program a GPU. However, I think what is really changing the game now is that NVIDIA has now a serious competitor on the market, that we see many HPC systems adopting this technology perhaps in the next 5 years. And so that the top 500 is not anymore very NVIDIA dominated. Hence, I brought you a short video that shortly summarizes what the AMD MI100 Instinct card is.
Today I'm excited to announce the AMD Instinct MI100. It's the world's fastest HPC GPU. It's our first CDNA architecture GPU. Exascale computing is going to give us the ability to realize all the advantages we hear so much about in the AI space, as well as the molecular dynamics research, pharmaceutical, energy research. All of those things will be advanced and move forward with exascale computing. We're really excited to be introducing our first generation AMD CDNA architecture GPU. The CDNA is just purpose-built to do computational math, and that's being realized with a nearly 7x performance improvement in FP16 performance, as well as nearly a 3.5x performance improvement over our prior generations. Tremendous results with this new architecture. The AMD Instinct MI100 is going to be the world's fastest GPU for HPC. It breaks through the 10 teraflop barrier, providing almost 11 teraflops double precision matrix multiply capability. The MI100 is the device that's on a path to an exascale. It also gives you all the capability you need to do your AI workloads, such as vFloat16 and FP16 low precision math capabilities. Along with MI100, we're bringing out our 4th generation software stack, ROCm 4.0, to support developers on this platform. In that stack, we're going to find all the key elements needed to do your software development, including TensorFlow, PyTorch, the most prevalently used AI frameworks, as well as compilers, OpenMP and our HIP compiler, and all the necessary math libraries for the commonly used applications. In order to make sure the MI100 works flawlessly for your systems and solutions, we've been working closely with our system partners Dell, HPE, Supermicro, and Gigabyte to bring these products to you.
Okay, I hope you got a little bit out of this marketing video. It was still a very interesting video, I think, highlighting here and there some capabilities of the system and also demonstrating the importance of the software that is also there. This would be an interesting time, an exciting time to see how that works. NVIDIA and basically coexistence of AMD now in the basically next couple of years. So that's all for the GPU lecture. As I said, we will continue lecture 10, especially in the practical lecture 10.1 and 10.2, more on deep learning, where we see that GPUs are adopted. But then every now and then we will come back to GPUs also in the subsequent lectures in lecture 11, 12, and so forth, and see where GPUs are really used as well. So that's really all for today. Lots of references. Lots of things going on for GPUs. Thanks for the team and talk to you next time.